Jacobian is actually a name. It's by a famous scientist. I think he was a mathematician, Jacobian, and he has many things named under his name. So what's the Jacobian? Well, I'll define it first. So the Jacobian is denoted by J. Okay, and here's what the Jacobian really means. So let's say that I have a function, and really this is not one function but many functions. So if you have many functions, you can put them as vectors, right? So f equals f1, and that's a function of q, and I'll define what q is in a bit, f2q, so on till fmq. So there are m functions, and I've put them together like in a matrix or a vector, if you like, and then q is the space of variables which f is a function of. So q could be x1, x2, it could be x, y, so on. So let's say that x1, xn. So given this, the Jacobian is defined as the partial derivative of df by dq. So note that f is a vector, q is a vector, f has dimensions m cross 1, q has dimensions n cross 1, and df dq has dimensions of m cross n. So I'm going to define it now. So that's df1 dx1, df1 dx2, and so on till df1 dxn. So this is the first row of the Jacobian. Then we have df2 dx1 df2 dx2 and so on till df2 dxn, and we keep doing this till dfm dx1 dfm dx2, so on till dfm dxn. So you can see it's m rows because we go from 1 all the way to m. And then because we have the partials from 1 all the way to n, the columns are n. Okay, so f is a vector, q is a vector, and the Jacobian is a matrix. Let's do a simple example and apply this in a simple example. So the example is, let's say f is x squared plus y squared. That's the first function, so f1, and f2 is 2x plus 3y plus 5. Q is here, as you can see, it's basically x and y. So then if I want to find the Jacobian or df dq, that's simply dx squared plus y squared divided by dx, dx squared plus y squared by dy, and then d2x plus 3y plus 5 dx, and d2x plus 3y plus 5 with respect to y. So if you take the partial derivative, which is basically when you take the partial derivative with respect to x, you keep y constant, you end up with 2x for the first term because y is in that case in the first term constant. Then when you take the derivative with respect to y, we have 2y. So for the second row first column, we have derivative of 2x plus 3y plus 5, that's going to be simply 2. And then the last term, row 2 column 2, it's going to be just 3. So this is the Jacobian of the function f as I showed you. Now there is a MATLAB function called Jacobian where you simply specify f, you specify q, and it'll give you what the Jacobian is. So this is how you do it in MATLAB. I'll show you a code how to do that a little bit later. Instead of shifting it now, I'll just do it later. So that's how you do it in MATLAB. Okay, any questions so far? Okay, so let's see how to apply this formula of the Jacobian in doing few things. So one of the applications of Jacobian is going to be finding the velocity of points. By points, I mean, if you want to find the velocity of the center of mass of a manipulator, then actually, okay, so a little bit of theory, and then I'll show you how to apply this to find the velocity of the two-link manipulator we talked about. Okay, so if R0 is the position of some point on the manipulator or any system, then we can write that position as a function of Q, where Q is the degrees of freedom. So for a manipulator, that would be theta 1, theta 2. Okay, and that F is basically that relation which we got by writing the position using translation rotation formula. So that's, so F comes from rotation and translation formula. Okay, so once you have a form for the position, let's take the, well, let's then find the Jacobian of this. Since we have f of q, we can write the Jacobian as df dq. Okay, so this is just the definition of the Jacobian. Now what I'm going to do is I'm going to multiply both sides by dq. So I get j dq is df. What I can now do is divide throughout by dt, and then the partial will become actually the complete derivative. So we have j dq dt equals df dt. And so I can write jq dot equals f dot, but f dot is nothing but r dot 0. So in other words, what I've written down effectively is that the rate of change of r, which is the Cartesian velocity, is equal to j times q dot. So one way of finding the velocity of any point is to take the Jacobian j, which is df dq, and then multiply it with q dot. We could also find that by doing, so if you see this, in the past what we have done is we've actually written down f and then just taking the time derivative of f. That's another way to do it, but here is another way to do it. So let's see how to apply this on the two-link pendulum we talked about earlier. Okay, so I'm going to draw the pendulum. Okay, so let's, the first link and then the second link. And this is theta 1. Sorry, this should be theta 2. Okay, and then the center of mass is here G1 and G2. And let's call this point the O, this point P, and this point Q. Okay, so given the system, the question is find the velocity of points G1 and G2, which is the center of mass. And we need that because once we find the velocity of center of mass, we can then use that in the Euler-Lagrange formulation to find the equations of motion. Okay, so how do we solve this? Well, we've solved this in the past by taking the derivative straightforward, but I'm going to show you how to use the Jacobian. So velocity of G1 is going to be the Jacobian of G1 times Q dot. What's Q dot? Well, Q is the degrees of freedom. So it's going to be theta 1, theta 2. And Q dot is simply the rate of change of theta 1, theta 2, but it's going to be omega 1 and omega 2. So the Jacobian times Q dot. So before we write that down, let's first identify what the Jacobian is. So as I said, the Jacobian is the rate of change of f versus q. Okay, so what's f? F is basically the position of point G1. So for that, I need to find the position of G1 in frame 0. And you should refer the notes. You'll see that the formula for the position of G1 is, let's see. Okay, you can use the formula, or you can actually do it by trig here. So the position of, let me draw the 0 axis, x0, y0. So position of G1 along the x-axis is simply C1 sine theta 1, and the y position is C1 cosine theta 1. Okay, so if you like, we'll call this x of G1, y of G1 equals C1 sine theta 1 minus C1 cosine theta 1. Okay, so this is your f. Okay, and then to find the Jacobian now, what you need to do is you need to do df dq times q dot, which is omega 1 omega 2. So I can write this down now as, since f is xg1 yg1, this is simply xg1 dx or d theta, sorry, 1, and dxg1 d theta 2 d yg1 d theta 1 dy g1 d theta 2 times omega 1 omega 2. Okay, so the rate of change of xg1, which is this term, with respect to theta 1 is simply c1 cosine theta 1. The rate of change of g1, which is this, with respect to theta 2 is going to be 0 because there's no theta 2 there, so 0. Similarly, rate of change of yg1 with respect to theta 1 is going to be c1, derivative of cosine is negative sine, so c1 sine theta 1. And then rate of change of yg1 with respect to theta 2 is 0. Okay, so here I have a formula for velocity of g1. It's c1 omega 1 cosine theta 1, c1 sine theta 1, c1 omega 1 sine theta 1. So that's my answer to the velocity of point G1. Is that clear? Any questions so far? Okay, no questions. Okay, so we can continue doing this to find velocity of G2. For that, I need to find position of G2 with respect to frame 0. So that would be x G20 y G20 equals. So what I would do is I would like you to fill this up. I would not, I'll do a couple of things here. I will leave blanks for you. So write the position, and this you can refer to the notes previously. Then to find velocity of G2, that's going to be jg2 omega 1 omega 2, and that's going to be from our formula which I wrote down here. It's going to be dx g2 0 d theta 1 dx g2 0 with respect to d theta 2 dy g1 with respect to d theta 1 dy g2 with respect to d theta 2 times omega 1 omega 2. Okay. Once you do that, I'm going to write the final answer, and you should check this with your own calculations. So if you do the math right, you will get VG2 equals, this is pretty long, VG, so it's omega 1 C2 cosine theta 1 plus theta 2 plus L cosine theta 1 plus omega 2 cosine theta 1 plus theta 2. So that's the velocity of the x velocity, and then the y velocity is c omega 1 L sine theta 1 plus theta 2. I think this is C2 plus L sine theta 1 plus omega 2 L. I'm missing a C2 here. In the previous one, C2 cosine theta 1 plus theta 2. Then I'm missing this C2 sine theta 1 plus theta 2. Okay, so check this. Okay, is that clear? Any questions on this? Question. Should we omega 2 with sine, right? Okay. So let me show you the code to do this little later. I'll show you the second application of using the Jacobian, and then we'll get to doing the MATLAB part, which is basically doing this using the symbolic toolbox. Okay, so that's one application of finding the Jacobian. By the way, you could extend this idea to find velocity of P, which is going to be dj of P q dot. You could also find the velocity of Q, which is djp. This should be jp, and then jq q dot. So you can find velocity of any point you want using this formula. Okay, so the second application is application 2. Is to find static forces. Okay, what I mean by static forces is if the system is in equilibrium, there are no accelerations of any length, then you can find what are the torques at the joints so as to keep the system in equilibrium. Okay. So normally what you would do is, if you did a course in statics, this is an undergrad level, then you would draw a free body diagram, and then you will do the sum of forces in the x direction equals 0 and sum of forces in y direction and moment equals 0, and that will give you a formula for the torques. You can actually do that without doing a free body diagram, as I'm going to show you next. Okay. So for that, I need a little bit of theory. to derive some expressions which then we'll use to solve for the equilibrium forces for a double pendulum. Okay, so this is based on what is known as virtual work, which you might have briefly heard in a previous class. So what you do is, if there's a system which is in equilibrium, it's not moving, then you displace the system by, so let's say there's a system, and then it's acted upon by forces F1, F2, and then there are some torques which hold the system in equilibrium. So what you do is you assume that the forces F displace the system by a distance dx and dy in the x and y direction. Okay, so these are not real displacements, they are virtual displacements. So then the work done by these forces is F transpose TR. Okay, so that's basically what is known as a component-wise multiplication or the dot product. I've not talked too much about the dot product, but what you do is you take the force in the x direction, you multiply with dx, you take the force in y direction, multiply by dy, and sum the two, and you get the net work done. So these forces are fx, fy, and these displacements, which are virtual, are dx, dy. So that's just an example. Okay, in 3 dimensions, it'll have one more dimension. So when this system has virtual displacement, there's virtual work done, these forces should be balanced by the rotational motion of the system. So this is again a virtual rotation. It's not real, but it's virtual. So the work done by the torque is going to be the torque times d theta. Okay, so this, all these dx, dy, d theta are virtual displacements or rotations. So that thing here is just again the dot product. So the total work done it says delta W is simply work done by the torque minus the work done by the displacement. And the reason for the negative sign is because one of them has to oppose the other, because the net work done is actually zero, and it's zero because again this is not real work, it's virtual work due to virtual displacement. So actually there's no real work done. So if you take this expression now and write it as d theta equals F transpose dr, let's divide throughout by d theta, so you get torque equals F transpose dr d theta. Okay, so you can see that dr d theta for a system like a manipulator is nothing but the Jacobian. It's the Jacobian because on the numerator you have the Cartesian position xy, and the denominator you have the degrees of freedom, which is theta. So that's similar as df dq. So we can write this as torque equals F transpose J. Okay, and we don't want to keep the transpose there, so we take the transpose on both sides. Taking transpose on both sides, we get torque. So the transpose of transpose is just the same matrix, is F transpose J transpose. Now there's a property which you did in homework 1, which is if you have A, B transpose, then that's same as B transpose, A transpose. So you need to switch the order. So it'll be J transpose, and then F transpose will come next, but it'll be transpose of F transpose, which is simply F. So eventually what you get is that the torque is J transpose. Okay, so that was what I was after. This is a formula to find the torque at the joints such that the system is in equilibrium due to the forces which I've shown. So now let's see how to apply this in solving for the static forces of a double pendulum. Okay, and this is going to be static calculation, not the Euler-Lagrange. Euler-Lagrange equations gives us the dynamic acceleration, so it's basically not a static problem. Okay, so let me reuse my figure. Okay, so let's assume that the manipulator is in a gravitational field and there's a mass m1, m2 of the two links. Because of this masses, the system is going to be torqued, and in order to hold the pendulum in equilibrium at angles theta 1, theta 2, there needs to be a torque which needs to be applied at the two joints. Right? Otherwise, the system will not be in equilibrium. So let's call that tau 1 and tau 2. So the question is, find the torques tau 1 and tau 2 such that the double pendulum is in static equilibrium. Okay, so this is where we can find the torque. One way is draw a free body diagram of the system. You'll have to draw a free body diagram for both links, solve for tau 1, then draw a free body diagram for the second link, that is G2, solve for T2, and you have the answer. The other way to do it is to use this formula which I just derived. The torque is J transpose times F. Okay, so let's see how to apply this formula. So what we have here is two torques. One is at link 1, other is link 2. And when we find the term J transpose F, it really means all the forces. So here there are two Cartesian forces. One of them is M1G and the other is M2G. So I would have two terms there, one for G1 and one for G2. So I need to write J of G1 transpose the Cartesian force at G1. So that's force is, the x component of that force is 0 because M1G only acts in the y direction. I put a negative sign to indicate it's negative in the negative y direction. And then I have JG2 transpose 0 minus M2G. Okay, so what remains is just to find the Jacobian of G1 and the Jacobian of G2. So Jacobian of G1 is D G1 dq, and Jacobian of G2 equals dg2 dq. Q is theta 1, theta 2, and G1 0 and G2 0. I actually wrote this down in my in the previous section. See previous section. In fact, I actually wrote down the formulas for these two Jacobians. So I've already done that calculation. I only need to sub in here. I need to take the JG1 and then take the transpose and simplify this. So let me just write it down. So if you look at my notes for the last section, the Jacobian was C1 cosine theta 1, C1 sine theta 1. So this is basically taking the transpose times 0 minus M1G. And then the second term is going to be, this is slightly longer. It is C2 cosine theta 1 plus theta 2 plus L cosine theta 1 C2 cosine theta 1 plus theta 2. So that's the first column. The second column is C2 sine theta 1 plus theta 2 plus L sine theta 1 C2 sine theta 1 plus theta 2. Then we have 0 minus M2G. So again, this is a slightly involved calculation. I won't recommend doing it by hand because the chance of making a mistake is high. You would use the symbolic toolbox to do it. So anyway, I actually did it using the symbolic toolbox, and the final answer is torque equals tau 1, tau 2 equals minus M1G C1 sine theta 1 minus M2G C2 sine theta 1 plus theta 2 minus M2G L sine theta 1. That's torque 1. And the torque 2 is simply M2G C2 sine theta 1 plus theta 2. So you can see that the torque 2, which is the torque on the second link, only depends on mass 2, which makes sense. Okay, so that's the answer. Okay. So again, I'm sorry, I was muted. Am I audible now? Looks like I'm audible now. Okay, so I'm going to provide you with two codes. One of them basically does the simple problem I talked about, which was finding Jacobian for simple expression. I'll do this using Jacobian, then I find the numerical value at a specific point, 1, 2. And then I also show you how to do it using central difference, which I talked about in the class on differentiation. And then I also have this other file, which will give you how to find the Jacobian of points G1 and G2 for the double pendulum. So running this, the first file gives me the same answer as what I got using hand calculation, and then the value at 1, 2. And then running this for the pendulum will give me the Jacobian formula, which I wrote down earlier. Okay. So that's pretty much what I have. If you want to do the torque calculation, you can also do it. I have not added it here. Okay, two things.